Hi, welcome back, my friends. This is William M. Briggs to another episode of Uncertainty and Probability Theory, the Logic of Science. We're on episode 54, Exchangeability and Parameters. Now, last week, if you recall, we did, over the past couple of weeks, we did the origin of parameters. We started with finite discrete evidence, and we saw where that went if we assumed our sample sizes go out to infinity. And at that point, once we get to infinity, at the very point of infinity, parameters come into being. Parameters, in ordinary probability models, we write things like this. This is a form of notation. This means our uncertainty in y is characterized by some probability model that is parameterized by these unobservable parameters. This could be multidimensional. All this stuff could be multidimensional. Sometimes you'll hear people say that little thing means is distributed as. It's strictly an error. It's always strictly an error. Nothing has a distribution because nothing has a probability. We spent the first 52 weeks trying to burn that into our brains. And I promised you we'd all forget that once we start moving into parameterizations and so forth. All of these probabilities and everything suddenly come alive again. And I'm going to beat that into our brains one more time next week. Because I promise you, you're going to forget all this. We could say y is distributed as some probability model. All it means is we're accepting as evidence this probability model with this parameterization. And those parameters are always just given to us almost all the time in these ad hoc models that we use. And somehow we think all of a sudden, because the model itself is ad hoc, and then we get confused. And so that's what I'm going to talk about next week. I'm going to go into that philosophy a little bit more. I don't want to talk about that so much right now. But we did see, when we start in a discrete and finite way, we had no problem. Everything was observable. There was none of these parameters. There was no arguments about prior distributions and posterior distributions and none of that stuff, because everything was discrete, observable, uniform, that is to say, finite, and it all worked out fine. It was only once we got out to infinity and we could let our sample size be as large as we like, just shy of infinity, and we didn't need parameters. So that's where parameters really come from. However, there are other seeming justifications for them, and that's this idea of exchangeability. And so I want to go through this. So something is exchangeable. It's very simple. So we have a bunch of statements here where we could think about these representing some proposition, whatever they are, propositions y1, y2, yn, given whatever evidence we're considering. If that is equal to the probability of y pi 1, y pi 2 all the way up to y pi n, given the same evidence, of course, where pi is some permutation. In other words, we take these indices and we just permute them. And there's, of course, lots of different ways and factorial ways we could permute these indices. And if the probabilities are the same for any permutation of these, this is called a permutation. And now that, before we just start thinking about that in general, before we understand what permutation is, I want to emphasize it is not the same as irrelevance. Now remember, irrelevance is our term for what some of the old school frequentist kind of way of talking, or Bayesian, of talking about independence, because independence is this language up here, where it's almost causal. And it's not if you're careful, but if you're not careful, which all of us tend not to be. For instance, I found today when I was today I worked out the math and not just copied and pasted from the book. I found a couple of more typos. Readers found a couple of typos I had last week. None of the conclusions change, however, but my enemies are always inserting typos. Today I think I have them all removed. Okay, so let's see why permutation is not the same as irrelevance or sometimes called, which I say incorrectly, of independence. I just don't like any term that smacks of causality when we're talking about. Causality is an ontological kind of a statement, and probability is an epistemological kind of a statement, as I've been emphasizing from day one. Let's think about these things called Polya-Earn models. These are simple. They all have, this is the problem, we have all these fancy names and all this fancy terminology with the pi 1, or sometimes they'll put the indices in parentheses and think, what's going on? And then people use all kind of weird notations and letters, special symbols and so forth, and you really got confused and think, this stuff must be incredibly sophisticated, when often it's just very short reminders of what's going on. That's all notation is. So you're always better served by thinking of the ideas behind the notation, and don't let the notation come to life. That's going to be the same in our models. Don't let the models come to life in your mind. That's the deadly sin we're always talking about. Anyway, a Polya model is very simple. There's a number of black and white balls in some urn. There's n of them, n white and m black. Very simple. And we'll call that our evidence. What's the probability of a white ball being drawn out first, given there's, if you allow me this kind of a shorthand notation here, what's the probability of a white ball being drawn out, given that there's n white balls and m black ones? We deduced how to do this from the statistical syllogism, which relied on the symmetry of logical constants, all very logical. Everything is deduced, no problem. Okay. So suppose the Earn model, that's not quite the Earn model, that's the beginning of it. Suppose we draw out a white ball. We look at it, we say, hey, that's white. And then we take another white ball from somewhere else and we dump that into the container. So if the first ball is white, then we have in the urn at time 2 still m black balls, and now we have m plus 1 white balls, and vice versa. If the first one we drew out was a black, we'd throw in another black and there'd be m plus 1 and still just n white balls. So now we can say, given now we want to know what's the probability of a white on the second one, given that we took out a white on the first one, and then there's n plus 1 and n plus 1 white balls and m black balls. Well, that's going to be very simple. M plus 1 over n plus m plus 1. And you can go on like this. That's the Earn model. But there's some interesting properties of this. This is the conditional, every probability is conditional, but this probability is conditional on the knowledge of the first draw. The first draw is explicitly written in here. And so we calculate this probability. This probability is fixed no matter what, because there's been no other draws. But what if we wanted to just calculate, I have to erase something. Let me erase this. This is a nice, short, sweet lesson, I hope, today. I'm always going on and on too long, but today I hope I don't. What's the probability of just a white? A white on the second draw, given we start with these conditions. Well, that's not the same as this, perhaps. We have to look. So another way to do that is to get a white on the second draw, that's the probability of a white on the second draw and a first with a white, or a white on the second draw and a black on the first, given our, evidence NM, if you like. Yes? I hope that's pretty obvious. And so that's going to be, there's nothing about these, so we can just add these probabilities. This will be the probability of white 2 given white 1, n and m, and n plus m. I'll just use that notation, you get the idea. So now we're going to actually have add a 1 because the white was the first one on the first draw, times the probability of a white 1 on the first draw. This is just cheating notation, but you get the idea. Plus the probability of a white on the first one, given black was the first one, with the NM just our notation you know, to write E to remind us how many balls we got in there, times the probability of a black one on the first draw, and I'll just start writing E because I'm lazy. All right, you get the idea. So in order to get the probability of a white ball on the second draw, we can get that by having a white ball on the second draw and a white one on the first, or a white one on the second and a black one on the first. Okay, simple enough. Oops. Well, I trust your memories are good enough about this. This is what I just erased. This is this particular probability, the probability of a white on the second given a white on the first is n plus 1 over n plus m plus 1. The probability of a white on the first we did up there is n over n plus m. Okay, now we can add these probabilities. A white on the second, given there was a black on the first, a white on the second, well, that's still going to be m, but it's going to be over m plus 1, because we add a black one, and there's now going to be n plus m plus 1 balls, and we only have n whites. And the probability of a black on the first is m over n plus m. And that whole thing equals, well, we have, we can take the n and the n plus m, factor that out. And then we're going to have an m plus 1 plus m plus 1 plus m over n plus m plus 1. And that, of course, is 1. So there we go. Aha! The probability of a white ball, which is what we started out here, the white ball on the second draw, given only our starting knowledge, is the same as the probability of a white ball on the first draw. Exactly the same. And that's because it's kind of intuitive if you stop and think about it for a moment. Basically, we're just grabbing balls out and we're putting them back in the same proportion, roughly, as those that were in there in the first place. And so as we go on, the probability, you can go, this is an interesting exercise. That'll be your homework. I stopped giving homework because not a lot of people are doing it. But you should be doing it. The white on any I, given the initial conditions, that's our, see, I'm so used to writing E. It's always going to equal n plus m. Interesting, right? So that this behaves like a regular urn in which we don't draw any out. That is to say, we don't replace any. We draw, or we replace them every time, but we don't add them. We don't add new balls to the urn. So it's pretty much like a regular urn, but it has different properties and all this kind of stuff. So why are we bothering with all this? That's the real question before us. Okay, because it's obvious that if we're talking about the probabilities of the white ball on the second draw, given we know what happened on the first draw, black or white, that's relevant information, right? That's relevant information. We need to know what happened on that first draw. That is to say, assuming we do know what happens on that first draw, that gives us information about the second draw. But it's just as obvious we could look at things like this. W1, B2 is equal to the probability of B1, W2, for instance. This right here is going to be the case. This is the result of this Polya-Urn model, in that these things, the order in which we draw them, if we're interested in the exchangeable, the order in which we draw them, we could calculate this probability W1, B2, or B1, W2. It's just like we did up here, calculating just for any WI. We can take this series however long we want it, and we'll find that this is an exchangeable probability. Okay, so that's not the same as irrelevance. Things can be irrelevant depending on how we consider them. And here, the order does not make any difference in how we calculate these probabilities. So there's a difference between exchangeability and relevance. That's all I wanted to prove. And so that exchangeability is a different kind of property, a different kind of way we're thinking about the knowledge. And so that's all that is. And so why is that important? Okay, because And here's the final, the grand finale of all this. Well, we introduced this term called exchangeability, and so you think to yourself, so what? I already got irrelevance. Well, irrelevance isn't enough. We need this idea of exchangeability. And that's because now we can assume, we're going to go back to here, we're going to assume that based on whatever evidence that we have, and we have some dichotomous white, we've been working with these dichotomous whites. Well, this was dichotomous too, black or white, yes or no, on or off, true or false, 0 or 1, however you like. Proposition Y, and we're going to assume that's the case. That's the evidence says that. Okay, no problem. And now we have an exchangeable sequence of Y1, Y2, Yn, which is part of, here's the kicker, this is part of an infinite series. Has to be infinite. Infinite series. Spelling does not count, so that means n's going off to infinity. If the series is part of an infinite series and it's exchangeable and these are dichotomous, that turns out to have this representation, this probability. I equals 1 to n of p to the yi, 1 minus p to the, is it 1 minus yi? D, Q, P. This is just each individual probability of y1 times the probability of y2 times the etc. That's all. That's multiplying those together, like in a anding fashion. Because the order doesn't matter, we could have this multiplication. That's the intuition behind this proof. I'm not going to prove this. It's take us too far afield, I think, because I want to emphasize. We will talk about this more when we get back to Jaynes. I keep threatening to bring us back to Jaynes, but I want to, before we start getting into the math a lot more, I want to make sure everybody has the ideas solid. It's the idea that counts, not some stupid calculation that we may or may not have made. That's not the important thing, or some typo in it, even less so. We want to understand what's going on behind these equations, because that's the important thing. The equations don't have life. We bring life to the equations. Anyway, that's the idea. If these things don't, the order doesn't matter. We can basically something like y1 times probability of y2 times etc. All right, and that's how we get this. And this right here is some probability distribution on P itself. That is to say, here's a distribution on the values of P. P can only be between 0 and 1. And it'll draw, this is a distribution right here, or a density. This is a probability density over here. I know we haven't talked a lot about these mathematically yet, but this is just the calculus here. And the most common one is to say this. Now, this is what's called an existence proof. I don't know why I'm waving that around. This is an existence proof. This happens. It doesn't matter what level of, what value of P it is. Even if we don't know P, this thing says this particular probability distribution has a probability for the observables and a separate probability for the parameters. And there's Bayesian statistics justified right there, because it says that there will exist a probability, the uncertainty, calculating our, or quantifying our uncertainty in these parameters. And the most it doesn't say, the problem with this proof, if you like, if you want to use the word problem, is that it's only an existence proof. It's not constructive. This part's kind of constructive. You can kind of see this. But this part right here is not. It doesn't tell us what shape or form this particular probability distribution on the parameter has. We don't know. It just says one exists. Now, and that leads some people to the wrong idea that there is a true one. That there's a true one out there. And then we start arguing about all kind of things. Again, we start with this ad hoc model, which has these ad hoc parameters, and then everybody starts arguing about what's our probability distribution for these parameters, forgetting that we pulled these other things out of thin air. I marvel at this. I don't understand this. But the most common one is just assume P could be any particular value, and we kind of did that. That's the limiting. We saw that in the last 2 weeks as we took our hypergeometric model for everything that was discrete and finite. We let that go to infinity, and that has the same kind of form as if this parameter where P at infinity goes to this theta, or whatever other Greek letter we like to use. Greek letters are always used for the parameters by habit and custom, nothing wrong with that. And Latin letters are usually used for observables or things that are known. Now, the whole thing about this funny thing was we assumed that we know what this P is. If we do, if we can deduce what this P is, we don't need this. That's the whole point. If we start discrete and finite and we can deduce this kind of stuff, this apparatus is interesting and nice and all, but we can deduce the exact form of what we want. We could have the exact probability distribution of any number of y's that we're going to observe before we've observed anything. We can calculate after we've observed some select few number of y's, the probability of observing any more number of y's that are yes and no into the future. We've done all that. And everything is discrete and finite. There's absolutely no arguing about parameters or prior distributions or none of that. That stuff only happens at infinity. And we saw when we got to infinity, that was only for the convenience sake of trying to come up with, and that math, we saw the hypergeometric and the negative hypergeometric as we let that stuff grow out. It gets big and ominous, and there's all kind of things go on, and you could make typos real easy in the kind of math. Once we write down these kind of like beta distributions and beta binomial distributions and stuff, the math is kind of really sweet and easy once you get to, I mean, you know, if you know calculus and all that kind of stuff, it's really simple. Combinatorics is hard. Calculus is easy. And so that's why we sort of start and go that direction. That's all exchangeability is. So again, if we start with exchangeability, which is not the same as irrelevance, we can prove these kind of existence proofs. But it doesn't tell us how to construct these kind of things. And in fact, I keep advocating people, this is a really huge, wide open area of research here. We can start with all of the common probabilities that we have that we want to use that are in our toolbox and so forth. And we could start in a discrete, finite way of looking at these. And then we can go out to infinity in different ways because it makes a difference which path you take to infinity. And we can deduce parameters from first principles. Now that would be fascinating. It's only been done for a couple of cases, and this is a perfect prime opportunity for any young mathematician out there that wants to do this. And we don't need this anymore, and we don't need any of this other apparatus, and we don't need the distinction between frequentism and Bayesianism. We just start right from logic and deduce our way forward. That's it. Okay. I have the corrected version of Chapter 8 at my websites, wmbriggs.com, wmbriggs.substack.com. There was I already erased it, but there was a typo. And a typo, all the words are correct and the conclusions are correct, but there was a typo in there. And I've corrected it on the blog and on the Substack, but it's not corrected in the book, unfortunately. That's it for now. I think either next time we talk more about this, if you're probably nauseated by it, maybe I won't say anything, and we'll do a normal, how do normal distributions come about? Well, there's the central limit theorem, that's one thing. And then there's also trying to deduce them from first principles, but there's some tricky bits because, and it's not a good idea, they start on the continuum. And starting on the continuum, meaning starting at infinity, is a very difficult thing to do. Any number of errors can creep in. Not typos, but conceptions and thought. Working with infinity is tough, and we're too glib with it. All right, that's it for now. Thanks very much for watching. See you next week.